So hello everybody. Just a few tests first. Let me just I'm connected with two devices, so I think it's my microphone is leaking through the other device. Let me try again.
I have
Victor, can you just say to me if the sound is leaking from my other device because I'm getting a kind of a reverb here because I have another device.
Can you hear me now?
Uh, yeah,
Okay. So right now I can't hear echo, but if I do, I will let you know.
okay. I think I think now, well, I don't know. Okay, I'm not using the other device now, so I guess we're good for now. Let me share the screen. Okay. Oh, the presentation mode is working for me in one device, but it's not working in the other device.
You can see the screen you've shared on your two devices.
Yeah, I have two devices connected, so I can see the screen I'm sharing through the other device. And I think in the primary device in my notebook, the presentation mode of the software is okay, but I don't think it's appearing for you guys as a presentation mode, right?
What I can see here is your slide, black hole, perturbation theory, and introduction,
Mm-hmm.
and that's all.
Yeah, but you cannot see the full slide, right?
Right. It seems just a part of it.
Okay, let me just.
I don't know if it is because you've shared only the application. Maybe if you share the screen, you can work or put the slide on full screen. Maybe you can adjust that.
Yeah, I think I share in the mode of window share. So I guess if I do this desktop share, it would be better.
Exactly.
Let me just try this. System desktop. Okay. Let me try again.
Yeah, so
Oh,
now we can see
there
everything.
it is. There
You
it
can
is.
also move the zoom bar on the top to somewhere. better. I don't know if you can put it more top of it.
The zoom bar.
Yeah, this one.
It is
I think,
oh, I understand. You mean to put it in another place.
yeah, another place or just more at the top of the screen. I think you can move it,
Okay.
drag and drop.
Oh
I,
my God, an old man confused with technology.
I believe if you put your mouse on the green bar, you are screen sharing, and then drag and drop it. It maybe can go,
Oh, okay.
yeah.
Now, now yeah, I guess this is
I-
the most top I can do.
On
But it's
the,
not gonna,
yeah,
okay.
okay, okay.
No, no, what are you gonna say?
Someone in the comments suggested that if you go to more on the top right corner,
Mm-hmm.
you can put hide
Mm-hmm.
video panel.
Oh, okay. Hide video panel.
Yeah. Nope.
Nope. Show video panel. Get back. So,
Mhm.
okay. Disable notations, hide names.
I think
Um,
overall, if you put this bar on the extreme right, and then
mhm.
if some element of the slide is hidden, we can just move again and can proceed like.
Okay. Okay, no worries. So well, here. So let's do this. So again, good afternoon to everybody. My name is Vitor Guimarães, and I'm going to talk to you a little bit about black hole perturbation theory. This is an introductory course, so I try to do a little bit of all the things that I've learned about black hole perturbation theory. And well, since that I don't know the background of all of you, so I try to do a little bit of a review first class about, on general relativity. I hope it will not be too dull for those who already seen it before, but I do this so that we can in principle have the same, at least the same vocabulary for the rest of the lectures, for the rest of the mini course. So if anything is troubling you, the sound, if I'm speaking too fast, maybe sometimes this kind of thing happens. I get too excited and then I start speaking too fast. You can always ask me to repeat it or talk a little bit more slowly. I don't know if the microphone is it's very good. I have a microphone that I will bring for tomorrow's class and the subsequent classes. But anyway, that's it. Let's do this. So we're gonna do some prefatory matters, and then we're gonna dive into our GR crash course. If you haven't seen general relativity before, it's gonna be a little overwhelming, I think, because I'm gonna have to cover a lot of ground in little time. So don't worry if you feel overwhelmed. Just I'm gonna point out the key elements that you're gonna have to keep in mind and remember for the subsequent lectures. So that's it. So let's go. So first, I wanna thank a lot of the organizers. So Nicholas that invited me here to do these lectures. I appreciate it a lot. I love the subject. I work with the subject, so it's a pleasure to talk about it. I think I'm learning together with you guys. I wanna I want you to see this as a group study instead of a set of lectures, because I'm also learning a lot as I do this. And Bruno Costa, I want to thank also, and Caio César Evangelista, Victor Lins, and organizers and people that are behind this. They are making this happen. This is very important. I think this is a very special event, the first of many, I hope. So, well, my introduction, I graduated here at the Federal University of ABC, and in physics. I got my bachelor degree here, and I'm doing my master's. So I'm working on my master's dissertation right now on gravitational waves of hairy black holes. So I've spent all my academic life so far here at the Federal University of ABC, and I guess that's it. Why we're here? Well, I guess this is a little bit over here, I guess would be better. Okay. Yeah, this is kind of annoying, but anyway, oh, here, I guess. Yes. So, why we're here? This is an exciting time for black hole physics and astronomy for so many reasons, and some of them because what was thought of as only another prediction of the Einstein general relativity, was became reality, right, in 2015 with the detection of gravitational waves by LIGO, and so far we have only been developing even more our techniques and working on other detectors to enrich, right, our data. And of course, more recently we got the black hole shadow image. So we are maybe not in the same footing as the golden age of black hole physics, but we are in a very exciting times to be talking about black holes, to be talking about gravitational waves, since we have now a new tool to probe the universe, to interact with the universe, and this tool is gravitational waves, right? So I want to call you everybody to this adventure we're gonna embark now. As you can see, this is a painting of Dante being guided by Virgil through hell. I'm not saying that perturbation theory is hell or comparable to, but my analogy is I want you to think of this, as I said before, as a group study, and all that I'm here for is to guide you through very a very convoluted set of calculations and references that don't always agree with each other. So I guess there's not a lot of things conceptually that are very new to everybody who has already seen general relativity before. But if you go if you go this by yourself, you may encounter some difficulties in some things that are not so much intuitive about the calculations and the references, sometimes for simplicity, sometimes because it's not of the scope of the reference. It doesn't cover a lot of the minute details about what is going on in these calculations. So I'm here to help you with this, okay? Everyone who has already seen general relativity can go to study black hole perturbation theory on his own, but I'm trying to save you some time. The main goal of this mini course is to give you some shortcuts, okay? And try to prevent you guys from, I don't know, wasting weeks and months, perhaps, trying to understand what the calculations are doing, which is what happened to me when I was learning this subject, okay? For the first time, at least. So let's go. The roadmap, as we're gonna follow it, is gonna be, well, we're gonna see perturbation theory one, which is composed by some elements of GR in the weak field limit. So if you have already seen general relativity, you have encountered this before, which is basically to assume that your space-time, your curved space-time, your curved geometry is nothing but Minkowski space-time, so flat geometry and a small perturbation, okay, plus a small perturbation, and open up the Einstein equations in this format. Then we're gonna see what it is to do perturbations in a flat background. So we're gonna disturb the Minkowski metric and see what happens to the equations of motion. And then we're gonna have to talk about a little bit about gauge symmetries, because they're gonna be very important to simplify our equations, because as you will see, linearized gravity, it contains a lot of elements. So equations that are long, that would they would be very, very hard to do if we had if we I mean, maybe very hard to do. Okay. So we have these gauge symmetries in GR that will help us simplify them a little. So we're going to talk a little bit about gauge symmetries, and then we're going to dive in perturbation in curved backgrounds, which is a very much more interesting subject. We're going to have to introduce tensor spherical harmonics. Maybe you have seen this before in some quantum mechanics courses, maybe not, but it's not. We're not going to dive in a lot on the details, mathematical details behind the tensor spherical harmonics, but we're going to present them, and we're going to present some properties that they have, so that we can make use of them and take advantage of these properties. And then we're going to do perturbations in Schwarzschild space-time. So we're going to do perturbations in a spherically symmetric and static metric, and see what the gravitational waves from this kind of space-time looks like. Okay, so let's go. We're gonna start. So first of all, I just want to see if there is any comments, any questions that you guys want to ask about the roadmap as it is. I don't know if you're curious about something, if you're gonna see something or not. I mean, because I know that a lot of you, I mean, I don't know, are interested in some aspect, and you don't know if this is gonna be covered here. So, well, if you don't want to ask now, you can always ask later, and I'm happy to answer any questions that you have. No? Okay, then. I guess
Vitor,
we're gonna. Yes.
someone in the comments asked if the
Okay.
presentation slides will be available somewhere.
Yes, yes. I haven't spoken with the organization about where or how to be available, but sure, I can make them available right after the lecture is over. No worries. Victor, can you help me with that later?
Of course, I will communicate with the guys and we can find a way to make this viable.
Okay. Okay. So let's go. Okay, so we're gonna do this GR crash course, which is not actually a crash course. I think of crash courses as a course that you see for the first time, and you and you absorb things, but I don't think that what we're gonna do here is very friendly to those who haven't seen at all anything of GR, at least in terms of really absorbing and getting fully the concepts. But at least you're going to get some vocabulary that will be useful for later lectures. But that's it. We're going to do some previously. just like the the start of a new season of a TV show. We're gonna do see what happened previously. So we're gonna base this review in two core principles of general relativity that are the Einstein equivalence principle and the principle of general covariance. Okay. The Einstein equivalence principle has a lot of ways to be stated, but the way we're gonna state the Einstein equivalence principle here is a more geometrical instead of physical approach. So what I mean by the Einstein equivalence principle is that when we start general relativity, okay, so we have a space-time manifold, right, which is the arena in which we're gonna do physics, and all our physics is gonna happen. So the space-time manifold basically models our universe. Okay, so if you people from mathematics, don't be angry with me. I'm gonna brush a lot of mathematical concepts here with very little concern for rigorous definitions. So bear with me. I'm trying to I'm trying to make this enjoyable, at least for a large group, a set of people. So we're gonna have to sacrifice a little bit of mathematical rigor. So let's go. So here we have our space-time manifold, this M here, this, and we have a point here in this space-time, P, and we have neighborhoods of this point, O and O prime here. And we have our manifold constructed in such a way that we have functions f and g, which are coordinate functions that are homeomorphisms that take these neighborhoods to a copy of Rn. Okay. And then this copy of Rn, the points that are contained in this neighborhood, they're gonna gain a tuple of coordinates, right? And we can do this more than once. If you have more than one coordinate function, we can map these neighborhoods into different copies of Rn, which will give to our points and neighborhoods different sets of coordinates. And by these functions phi, which is the coordinate transformation, we can relate these sets of coordinates from the Rn to the Rn prime here, which is also another copy of Rn. Okay. What I mean then, what the Einstein equivalence principle means is, geometrically speaking, at least, one of the things that it means is that our space-time may not be flat globally, but locally, he's always homeomorphic to Rn. Okay, so locally, our space-time is always flat, and we can do physics like this because we know how to do calculus in Rn. So when we're gonna do calculus from the later lectures, what we're actually doing is taking what it is happening in the manifold, taking them to copies of Rn and doing calculus there and coming back, right? Because these coordinate functions are one-to-one, they are invertible, and so on and so forth. Okay? And the principle of general covariance basically means that physics must be the same regardless of the reference frame we're working. So that's why we have these coordinate transformations here, so that we can be okay with doing physics and not have to worry about the reference frames, because we're gonna be working in a framework that transforms, and with objects, which are the tensors, which transform in a way that maintains the objects fully invariant under coordinate transformations. Okay, so we're building here a framework that is invariant under coordinate transformations, and let's do this. We have to construct the spaces where our vectors, scalars, and tensors will live. So this is our manifold. So I want you guys to imagine that we have a real line here, and we have functions gamma that map the real line into our manifold, okay? And this curve gamma is parameterized by this parameter gamma, is gonna map the real line into the manifold, and the image of this mapping is this red curve here, crossing P. Okay. We're gonna and you're gonna see, sorry, you're gonna see that we can define at P the tangent vector of this curve here. So we created this curve by this mapping. And at P, we can always define the vector that is tangent to this curve at P, okay? And we can do this for as many curves that we want. So we have another mapping here, psi, that does the same thing. So he maps the real line into the R manifold, but since it is a different mapping, it will be a different curve. And this curve at P will have a different tangent vector, which is this vector here, this green vector. So we want to do, what we want to do is take the set of all the vectors tangent to curves that are crossing P, okay? All the curves that cross P here. And we want to take the set of all the tangent vectors of all possible curves at P, and we're going to define a vector space here, okay? And see, as I said before, everything we do in our manifold can be mapped to copies of Rn, right? So here we have a copy of what's happening in the neighborhood of point P. So you see, we're going to have the vectors here, and here in the other copy of the Rn, another copy of Rn here. So we can do calculus with these vectors and define things with these vectors in a place that we know how to do this, right? Which is the Rn. And here we'd have the coordinate transformation that would translate the coordinates that these vectors here have in this copy of Rn to the coordinates that these same vectors have in the other copy of Rn, okay? So we define what we call the TPM, which is the tangent space at P, element of M, which is the vector space which contains the tangent vectors to all curves passing through P with basis vector mu. I'm not gonna prove to you guys that we can use the partial derivative here as a basis vector, but you can check Carroll, Space-Time and Geometry, the book by Carroll. And I mean, you can check any of the references that we cited at the website for the mini course. The proofs are contained there, but I think it would rob a lot of our time. So I'm not actually doing this here, but I'm gonna have to have you believe me and trust me on this, okay? So we define the tangent space at P, right? Which is which we can prove that is a vector space, okay? Another proof that I won't do here. But yeah, in introducing the tensor product operation here, which is this symbol here, we can create other vector spaces, which we will call the TPS, which stands for the tensor product spaces, which basically means that we are using these vectors to create what we will call the tensors, okay? So we are combining vector spaces, okay? We are combining TPMs to construct what we will call the KL tensors of our manifold, okay? So here the tensor product spaces are vector spaces formed from the tensor product of two or more vector spaces defined at a point P. P, which contain the KL tensors T, okay? And these tensors, these KL tensors T can be represented like this, okay? So the actual tensor is this bold T. The T with these indices, upper and lower indices, are what we call the components of the tensors. And here we have the basis vectors, okay? Here we have the partial derivatives as the basis vectors for our vector spaces. And here the dx's are the basis vectors for our dual vector spaces, right? One can prove, and I think this is very intuitive to see that that this basis vector is what takes this basis vector to the real numbers. So this, given that this is the basis for our vector space, so it becomes easy to see why we would choose this to be the basis for our dual vector space. Okay. So then if you take V, if you take, if you take the TPM we constructed here, and you do the tensor product operation of it with itself, you would have a tensor, right? That will be the combination of two. If you combine it 3 times, you're gonna have a order 3. If you combine one vector space with its dual, we're gonna have a 1-1 tensor, and so on and so forth. Okay. These tensors, they transform in a way that the important thing here is that this object here, the bold T, stays invariant under this coordinate transformation, okay? So what happens to the coordinates here, to the components, the components are going to transform like this, okay? And as you may assume, and you'd be right to do so, the transformation law of the basis vectors would have exactly the inverse form, so that when we apply the transformation to the components and the transformation to the basis vectors, they would cancel each other, right? So we're gonna transform this by some gamma and this by gamma inverse. So which would mean that the object T, bold T, would stay invariant under any coordinate transformation, okay? Which is exactly what we're doing here. So T tilde is equal to T, which is exactly what we want and what the principle of general covariance demands, okay? Also, all these tensors can be decomposed as in a symmetric and anti-symmetric parts. So this is the anti-symmetric part of the 0-2 tensor here, T. So yeah, is some sort of an abusive notation, because we're calling this a tensor now. We were calling this a tensor, but since whatever happens here induces what was going to happen to the basis vectors, so we're going to throw all this away and look only at the components, okay? So here we have a tensor T mu nu, which can be decomposed into a anti-symmetric part and a symmetric part, okay? And this would mean that to call some tensor symmetric would mean that the anti-symmetric part of this tensor is equal to 0. And the same would happen for anti-symmetric tensors. So for a tensor to be anti-symmetric means that the symmetric part of the tensor is equal to 0, okay? In such a way that all that is left is the anti-symmetric part, and the same for the symmetric tensors. The only thing that would be left is the symmetric part, okay? And here we define what it means to be symmetric and anti-symmetric. So this represents what is symmetric, with anti-symmetric, sorry. And this with what the symmetric part means. So basically, for a tensor to be symmetric, the anti-symmetric part would have to be zero, which would mean that if you trade indices here, the tensor is the same. The component would be equal and with the same sign, right? This equal to zero would mean that T mu nu is equal to T nu mu. Okay. And for a tensor to be anti-symmetric would mean that the components T mu nu are exactly equal to minus T nu mu. Okay, so a component T01 would have to be equal to minus T10, and so on and so forth. Okay, let me just move this. Okay, so now we're gonna have to introduce a new operator, which we will call the covariant derivative. And the motivation for this is because our current derivative operator, the partial derivative, maps vectors to objects that don't transform as tensors. And that is a problem, right? So if you check this, so what we're doing here with the primes, it means that we are doing a coordinate transformation. And if we follow the transformation law that we did here, that we presented here, we're gonna see that this object does not transform as a tensor because of this red term here. This red term here spoils the tensor transformation law, which would be only this. So we have to do something to correct this because otherwise we wouldn't be allowed to perform derivations and any calculus. So let's go. Let's define a new derivative operator. So the derivative operator requisites that this new operator must obey. So it must be linear, right? It must obey the Leibniz rule. It must map KL to KL plus one tensors, right? Which is exactly what the partial derivative does with scalars, right? So if you take the partial derivative and act the partial derivative in a scalar f, you will see that the correspondent, the image of this mapping would be del mu f, right? So this means that we are mapping a 0, 0 tensor, right? A scalar into a 0, 1 tensor, which would be a one form, okay? So this derivative operator must do this also. It must map KL tensors to KL plus one tensors, right? And it must reduce to the partial derivative when when acting on scalar functions, right? Because the problem is not on the action of the partial derivative on scalars, but when partial derivatives start to act on vectors and tensors of higher order, higher rank, I mean. Okay, so we're gonna look for a derivative operator that, well, that does all these things. Let me just check one thing here. If okay. Okay, so I'm looking. I have the meeting chat opened in my other device. So if you guys wanna send questions as I speak, I can see it, and Victor doesn't have to interrupt and keep telling me. I'm not gonna give you too much work, Victor. So I now I can see the meeting chat. But if I miss anything, please interrupt and please warn me. Okay. Okay. So let's go. So the intuitive approach would be to start from the partial derivative and try to correct it somehow, right? Do some add or subtract something that would take care of this inconvenient part here, this inconvenient extra object that is spoiling or our transformation law. So we define here what we call the covariant derivative, okay? And this object C is going to take care of extra elements that and fix our derivative in so that we can have all these requisites met, okay? So as I said, this is gonna take care of the red terms in the previous equation and make sure that our new object transforms as a tensor. So, but the problem is that for it to do so, this guy is gonna have to obey a different transformation law. So this comes to at a cost, okay? So if you do the transformation law, all right, so the detail behind this calculation, so you perform the tensor transformation law here, assuming that it must transform as a tensor, and see what the form of the transformation of this object must have so that this would cancel, okay? And the answer is exactly this in equation 10. So as you can see, this object does not transform as a tensor, right? So is the price we have to pay for our new object with the covariant derivative to transform as a tensor. So, okay. With this object, we have a derivative operator that satisfies all the aforementioned requisites, okay? It is linear. It obeys the Leibniz rule. It maps KL tensors to KL plus 1 tensors, and it reduces to the partial derivative when acting on scalars, okay? This is another operation, another set of operations that I won't prove here because I think it would take a very long time to do so. And you can always check Space-Time and Geometry or the book by Ferrari and Paulo Pani, or I mean, any general relativity textbook of your choice. But I very much like Space-Time and Geometry. And I'm sure that you can see all these properties, the proof that this operator meets all these requisites in there, okay? So let's move this here. Okay, so in the case where the corrected derivative operator is the partial derivative here, in which case this guy
Ok. Agora deixa eu ver se eu tô
transform.
passando a...
Vitor,
Yes.
I'm not sure if you replied to a doubt in the chat, but someone asked why L to L plus 1, but not K to K plus 1.
Okay. Okay. So if we look here, thanks a lot, Victor. If you check here, what we're doing, because this derivative operator is defined like this. Okay, so the intuitive form for you to see, I think it was João Pedro that asked this. So if you check here, what we had previously was this tensor T nu, right? And we act the covariant derivative. So if you look at the object as a whole, you're going to see that you have one covariant index and a contravariant index. You had only one contravariant index before, but now you have one covariant index also. So you went from a tensor that was a 1-0 tensor to a 1-1 tensor, right? Here in the when we act the covariant derivative in this tensor. If we acted, instead of acting the covariant derivative in a contravariant tensor, if we acted on a one form, so if this index was lowered here, we would have a 0, 2 tensor as an image, right? So previously we would have a one form or a 0, 1 tensor, and acting the covariant derivative would give us a 0, 2 tensor. So the covariant derivative in this definition always increases the number of covariant indices, right, in the object. That's why we are we're mapping KL tensors to KL plus 1 tensors and not K plus 1 tensors. Does this answer your question, João? Okay. I mean, you're gonna see a lot in the subsequent lectures this derivative with the upper index, which would mean that we are increasing the number of contravariant tensors, but it's completely analogous, right? Because the only difference from this with the upper index and the lower index would be the action of the metric, which I'm gonna present to you later. But you can define I don't think there would be any problem to define the covariant derivative with the index here. I mean, with the upper index. But I think it would just confuse everybody. So I think it's completely analogous, but we are defining this way. So this is what we have, and the reason behind this is exactly the way that we defined the covariant derivative. But moving on, so this guy does not transform as a tensor, and this new covariant derivative obeys all the aforementioned prerequisites for the derivative, for the new derivative operator. So the fact is that there are a lot of different covariant derivatives that one can build, right? So if you have studied particle physics, you're going to see a different kind of covariant derivative in that context, right? When you're studying particles. But for our purposes here, so for our purposes here, the covariant derivative of interest in general relativity so far is the one in which the derivative operator that is corrected is the partial derivative, right? And that in this case, when the corrected derivative is the partial derivative, in which implies that C transforms like this, then we would have that this guy would equal what we call the Christoffel symbols. Okay, so if you go to the book by Wald, General Relativity by Robert Wald, the treatment that he follows in that book is more a little more broad, right? Because he considers all the possible different derivative operators that you could be quote unquote correcting. So this is why this guy at first is not the Christoffel symbol, but since we identified the corrected derivative operator as the partial derivative, this guy will transform as we showed earlier, and in this case, this guy equals the Christoffel symbols. Okay, so such that the action of the covariant derivative on arbitrary tensors would be as follows. So here are the rule of how this covariant derivative acts on arbitrary tensors, or KL tensors, right? So you see here that for any arbitrary KL tensor, we're always gonna take the partial derivative, and we're gonna add terms multiplied by the Christoffel symbols for every upper index, so for every contravariant index, and subtract a term multiplied by the Christoffel symbols for every, and contracted with, and here also contracted, for every single covariant index, okay? For details, I'm going to repeat this a lot in this lecture. For all the details about these operations, you can check in the books that I said before. So space-time and geometry, WAD, and so on and so forth, right? The treatment is very straightforward, is not very hard to follow, but I have a lot of ground to cover in this lecture. So unfortunately, I cannot go into details, but I mean, that's it. Let's go. Let's continue. So, okay, there are very different approaches to present the connection. Some books, some references, they present the covariant derivative first and the intuition behind the covariant derivative first, so that we can talk about the affine connection. But the affine connection is completely independent from a notion of covariant differentiation on a manifold. So some books, like the book by Adler, for example, he introduces affine connections first. But anyways, we are following the structure, the train of thought, very similar to that of Carroll. Okay, so we need to approach another problem of ours, because we defined the tensor space, the tensor product spaces, and the vector spaces. All we defined so far, we defined at one single point, at each point of our manifold, right? But we don't know how yet to connect these points, how to compare tensors, vectors from different vector spaces, from different tensor product spaces defined at different points. We have no way of doing that yet. So to do so, i.e. to compare tensors at different points on our manifold, we need a notion of a parallel transport on M, right? Why? Because the way we're going to do this is we have curves. We know how to deal with curves in our manifold, right? Curves in our manifold are nothing but mappings from the real line, right? Remember? So we're going to use these curves in our benefit and tangent vectors, which we already defined and we know how to deal with in our manifold, to build some kind of a connection, which is very intuitive by the name of the slide, a connection between these vector spaces, all right? Well, a way to compare the TPMs to the TQ, to SMs, to LMs, and so on and so forth. So equipped with the notion of covariant differentiation in a given coordinate system, and a curve x mu with parameterized by some parameter lambda, we define this, which is a kind of directional derivative, right? The capital D here is taking this vector, this contravariant vector here, T mu, and what it does is it takes its covariant derivative in the direction of the tangent vector of the curve x mu, right? Here is the definition of the tangent vector, right? So if you have a curve x mu, you take its derivative with respect to its full derivative with respect to lambda, and we have the tangent vector of that curve. And analyzing this derivative at a given point, we have the tangent vector at a given point, okay? So what this derivative does is it takes its covariant derivative in the direction of the tangent vector to the curve, right? So we are transporting this vector along the curve x mu, right? Okay. In such a way, we define this operation of the directional derivative in such a way that if this covariant directional derivative here is zero, it means that, well, it means that the vector didn't change, right? You take the derivative with respect to some curve and the vector doesn't change. So this means that T mu was parallel transported under this curve. We could change the curve, right? We could change by some y mu parameterized by some parameter tau and do the same operation and obtain a different result. So a vector is being parallel transported under one curve does not mean that it will be parallel transported under another curve, right? So this is what we mean by parallel transport under some curve, right? Which means that you take the directional derivative with respect to some curve. And if this directional derivative is equal to zero, then the vector, the tensor, T mu, a KL tensor, arbitrary tensor, is parallel transported if this directional derivative is equal to zero. If we open this expression, so we use the definition for the covariant derivative here, right? We obtain this equation, and we see that the notion of parallel transport is intrinsically related to the Christoffel symbol, right? Because to obtain a notion of parallel transport, we needed a covariant derivative. So to do so, we needed to correct the partial derivative, and we did so with the Christoffel symbol. So with the Christoffel symbol, we were able to construct a covariant derivative. With a covariant derivative, we constructed a notion of parallel transport, and now we have a way to compare tensors at different points. And we're gonna, in the way to do so is to use the curve, right? Connect 2 points with this curve and see what it would be if the tensor was parallel transported. But I think I covered this a little in a bit more detail. But the fact is that for me to construct a notion of parallel transport, we needed the Christoffel symbols. We needed what is called the connection, right? So the Christoffel symbols also have this other name in general relativity, which is called the connection. Okay. Okay, I think I didn't put this in the class, but the thing behind parallel transport and the fact that we can now connect the two tensors is, connect and analyze tensors at different points, right? Because that's the problem. We have tensors defined at one point, but we don't know how to analyze the same tensors at a different point. But now that we have a notion of parallel transport, we can transport this tensor, right, through this curve. It can be parallel transported or not, but we always compare the tensor at a different point Q with itself if it was parallel transported, right? So we do parallel transport 2 times. We do under some curve, and we do under the curve that parallel transports it. The difference between the real vector, the real result of the parallel transport, and what it would be if it were parallel transported, this is what the covariant derivative measures. Okay, we can go into details after class if this wasn't clear, because I know that it's very abstract, and I could do some, I don't know, we could do some images. I could draw a little so you guys could have a more intuitive picture. So, but let's do this after class so we don't get too much behind schedule. Okay. It's 5:08. Okay, so let's continue. Just a question, Victor. I don't I remember seeing in the website that the classes would stand from 4 o'clock to 7 to 19, from 16 to 19. Is that the runtime of the total runtime of the lectures, or is there some other constraints on the time? Because Nicholas had given me another different information. Victor, are you among us?
Yeah, sorry, my connection was bad. Can you repeat?
Yeah, so Nicholas had told me something about the runtime of the lectures, but I'm just confused because in the website I had a different information about until which time it would be.
So on the
Okay.
website, I saw that
Mm-hmm.
the lecture would start at 16 at BRT,
Mm-hmm.
and
Mm-hmm.
theoretically, if the workload is 10 hours for 5 days, it's 2 hours a
Mm-hmm.
day. So you could
Okay.
go until 18.
Okay. Okay, that was what he said to me. In the website it goes until 19, so I was a little confused. But okay, I think we can keep this to 18. This lecture is gonna be very dense, guys. So because we have a lot of ground to cover in this lecture, but I promise that I try to maintain all lectures in the 1 hour and a half. Maybe a little more, maybe a little less. But okay, so let's continue.
Just to clarify, Vitor, the reason why in the
Mhm.
website there was 16 and 19 is because of the time zones. It's 16
Oh,
BST
okay.
and 19 UTC.
Okay. Okay. That clarifies a lot. Thank you. So let's keep going. So now we're going to present maybe the most important tensor in our space-time, which is the metric tensor, right? Which is a symmetric 0-2 tensor G, which contains the essential information on the geometry of our space-time. Okay, what I mean by that, what I mean is that G, there are a lot of approaches on how to describe G, but basically G is responsible for teaching us how to take inner products between vectors in our space-time, right? So for it to be able to do that, it has to contain information on the geometry of our space-time, right? So G mu nu, which are the components, which we will interchangeably call the tensor G mu nu, gives us a dynamical notion of distances, right, in our four-dimensional curved space-time. Because through the components of tensor G, we are able to define the line element. And what the line element translates to us, it's exactly the notion between distances in our space-time. Since we have a curved space-time, the notions of distances are dynamic. What I mean by that is that it changes, right? With the space-time coordinates. So what I mean by the distance between 2 points in some region of space-time may not be the same as in another region of space-time, right? So with the metric tensor, we are able to construct the line element, which is basically recalibrate our rulers, right? In first courses on relativity, people always say that you have clocks and rulers, right? What the line element says is how to calibrate our clocks and rulers so that we can make measurements in different points of space-time, not only in different points, but in different coordinate charts, in different reference frames, right? And compare them somehow, okay? All right, so we have here, note that the ds, the line element, is a covariant form to measure distances in our spacetime, right? Because this object here is completely invariant under coordinate transformations. One can see this because G mu nu is a 0-2 tensor, which means that it transforms with a transformation gamma, but this object here, dx mu, dx nu, it transforms because it has two contravariant indices. It transforms exactly the inverse way, which means that this object here is invariant under coordinate transformations, right? For you guys that haven't encountered general relativity before, one trick is to see that these indexes are what we call dummy index, right? Because this index here is contracted with this index here, which means a sum in Einstein notation, right? I hope you guys have seen Einstein notation before, which means this would be a sum of the G00, dx0, dx0 with G01, dx0, dx1, and so on and so forth. So one way to see that this is invariant is to see that we have no free indices here, right? This index is contracted with this, and this is contracted with this. So we have no free indices here, which means that this guy is completely invariant under coordinate transformations, okay? Garrock, which is also very good reference, notes on general relativity, calls this the space-time interval, okay, which is an invariant, okay? So distances, spatial distances between points and time distances between events may not be the same in different reference frames, but the space-time interval is something that different observers will always agree upon, okay? All right. So, yeah, the metric tensor is also responsible for connecting elements from one vector space. Remember the TPM we defined in the start of the lecture with its dual vectors, right? How it does that is it takes a vector, right, from TPM, which is this tensor, this contravariant vector T mu, and it gives us the exact correspondent, right, in the dual space TPM star, right? So note that contravariant vectors live in TPM and covariant vectors live in the TPM star, right? And the map between the two are exactly the metric tensor, right? The inverse does exactly what you would expect from an inverse mapping, which is to take covariant vectors to the contravariant vectors, to its contravariant correspondent, okay? So we see here that the metric tensor takes contravariant vectors to its dual vectors, which are the covariant vectors, and the inverse metric takes covariant vectors to contravariant vectors, okay? Here we define G mu nu with the upper indices as the inverse metric. And what we mean here in practice, in terms of what we call the index gymnastics, is the metric is responsible for raising and lowering indices. Okay, that's what it does. I mean, visually is what it does, right? But behind the scenes, what he's actually doing is connecting vector spaces to its dual. Okay. Yeah. So you could ask, is this covariant derivative, and by consequence the Christoffel symbols, uniquely defined? Well, you could ask that, and you know from what I said previously that it is not. You can define different covariant derivatives for your space-time, right? Which would mean that you would, for this different covariant derivatives, you would have different connection coefficients, right? But even though this definition is not unique, there is only one that satisfies this equation. So if you have a covariant derivative, if you have a metric, there is one and only one covariant derivative that maps the metric tensor to zero, right? And this is what we call metric compatibility, okay? Metric compatibility means that our covariant derivative, the covariant derivative of our metric is equal to zero, right? Which is basically to say that our metric is parallel transported along our manifold, all right? Is always parallel transported along our manifold, okay? So we say that along with all the prerequisites of the derivative operator, nabla mu also is metric compatible, okay? If it satisfies this equation, okay? This means that we can define our connection coefficients in terms of G mu nu, right? By doing so, right? You can see the proof of this in Carroll, in Wald, but we can define the Christoffel symbols as this combination of partial derivatives of our metric contracted with the inverse metric here, right? And this is the definition that we will use for the subsequent lectures. So for you guys that were waiting for what is important to keep, yeah, this proof is very nasty. Yeah, yeah, you should. I think it creates character, right? It creates character. If you haven't done it yet, you have to do it sometime. It's the same thing with the Schwarzschild metric, right? Getting to the true form of the Schwarzschild metric by hand, doing so in your own accord, it creates character, right? It's something that you will never have to do again in your life, but it's good that you do it at least one time when you're learning general relativity, right? These proofs are very, very, very tedious and nasty to do, but they are important so you can at least practice the index gymnastics, right? Practice how to manipulate tensors and so on and so forth. But this is a definition that is good for you guys to keep in mind. Yeah, yeah. We all been through that. We all been through that. We all been through that for certain. If you haven't, you will eventually. It is, winter is coming, right? But okay. So this is a definition that it is important for you guys to keep in mind, because this is going to appear again and again and again in the lectures that are to come. Okay, this definition of the Christoffel symbols in terms of the metric tensor. Okay, So we're not doing homework in this mini course, but I guess one that you could do, you could impose on yourselves is to do this proof. This proof is very important. Okay, so you see that we could have started all this, right, with the metric, defining the metric tensor, and then through the metric tensor, defining the affine connection, right, that makes the covariant derivative metric compatible, and then with the new definition of a covariant derivative, define the parallel transport, and then with the notion of parallel transport, determine the motion of freely falling bodies. Why I say that? Because if we get back to that directional derivative that we've done before, right? Remember the directional derivative of t if t is parallel transported by this curve, right? So we could say that this t mu nu is equal to its parallel transport to well, excuse me, please. Sorry, I got a little mix up here. So we get this directional derivative here, and if we trade t mu, right, by the tangent vector dx mu, where lambda is an affine parameter, we get this, right? All we've done is, let me get back to that slide. Yes, this slide. All we did was set this equal to 0, right? And trade t mu with dx mu d lambda, right? So we identified t mu with dx mu d lambda. And this equation here becomes this one, right? Which we call the geodesic equation, which is basically saying to us is, if you have a tangent vector, right? So if you have a curve, x mu, such that the tangent vector is parallel transported along it, then this curve is what we call a geodesic, right? I'm going to say it again. So you take a curve, if you take its tangent vector, if you transport the tangent vector along its curve, its own curve, and this vector is parallel transported, right? So if you take the derivative of this tangent vector along the curve to which this tangent vector is tangent to, and this vector is parallel transported, i.e. this directional derivative is equal to 0, this curve is said to be a geodesic. So geodesics are curves that parallel transport its own tangent vectors, okay? In a physical way, is to say that this curve represents the movement, right? The path of freely falling bodies in space-time, which in general relativity means that this body is completely free of external forces, right? So this body is completely free. He's traveling through space-time, not worrying about anything, and so on and so forth, okay? So free particles travel along geodesics, right? So we see that GR is always translating geometrical notions into physical ones, right? This is why some of us, at least, like to think as general relativity as a geometric theory more than anything else, right? All right. So what we're going to do next is to define what we mean by curvature, right? We're talking about, space-time and curved space-time, but what we mean by that and how can we attest if our space-time is curved or not, right? So I like a lot the analogy that some books do. that is, imagine that you are an ant walking in a basketball, okay? So all your notion, all your universe is completely two-dimensional, right? I mean, your reality is two-dimensional. So in your reality, in your frame, is very difficult to ascertain if your universe, right? If the ball in itself, in the analogy, is a curved manifold or not. So what we're gonna do here is develop a way to do this, right? A experiment that this ant could perform and see if the universe, right? This basketball is curved or not, right? Which is to say that we are focusing in the intrinsic qualities of curvature instead of the extrinsic qualities of curvature, right? What I mean by that, well, if you are a human being, right, and you take the basketball in which this ant lives, you can clearly see, trivially see that this ball is curved, right? That it possesses curvature. But this is a way that your brain is interpreting, it already contains notions of extrinsic curvature, right? I mean, the way that the ball is embedded in higher dimensions, right? But this ant has no way to do this because its whole reality is two-dimensional, right? So it has no concept of this extra dimension that would help her see that this ball is curved. So it needs a intrinsic notion of curvature, right? And this test that I'm gonna show you guys now is an experiment that this ant could perform, and it would give her the response to which this surface that it is walking on, it's curved or not. Okay, so you take a vector t mu, right, defined in a certain point P in our manifold, and we're gonna transport it along two different paths. Okay, so first we're gonna do it along this curve here, right? And then we're gonna do it along the other curve here, the curve that is described by this index mu here. So we are taking the derivative with respect to mu first, then with respect to nu later. Then we're gonna take another derivative with respect to the same curve in the opposite direction here, and then we're gonna take it back to the initial point, right? If I do this with this tangent vector, right, t alpha, if I perform this closed loop, and when I return to P, this vector is unchanged, completely unchanged, which means that it comes back in the same vector. This means that that this surface is flat. Okay, so the presence of curvature is obtained by the difference between the transported vector and the initial vector, right? In this image here, we did this, right? We did this closed loop transportation here with the notion of parallel transport that we know. And we see that when we got back to P, the tensor, the transported tensor, the transplanted quote unquote tensor, as Adler likes to put it in his book, the transplanted tensor here is not the same one, right? There is a tensor there is a vector that I can connect these two here, the difference the vector, which contains the information about the curvature here. So it means that this surface is curved, right? Because I transported in a closed loop and it came back different, right? Mathematically, we can do this by taking the commutator of the covariant derivatives with respect to mu in respect to nu. When I say covariant derivative with respect to mu and covariant derivative with respect to nu, what I'm actually saying is that I'm taking parallel transports with respect to two different curves, right? Okay, so if we take the commutator, right, which is exactly this, look that it's exactly describing this first term here is describing this and then this, right? So the transplantation of t to this point here, right? So we transport it through here and then here, and we get the tensor t alpha here. But then the second term with a minus sign, because we're taking the inverse direction here, is exactly doing this and this, right? Is exactly what it's doing. It takes this first and then this, right? So I hope it is clear. If it's not, you can put it in the chat, right? If it's not clear that this mathematical expression translates exactly what I just told you here with the picture. If it's not clear, we can clear this up later, okay? But then what we're gonna do here is open up this covariant derivatives with their definitions, right? And what we get is this. This is another kind of nasty calculation that one can do to try and fix the rules of index gymnastics and so on. But what we get is these two objects here. We're going to call this object a tensor R, which is a 1,3 tensor, right? One covariant index and one contravariant index, sorry, and three covariant indices, right? Multiplying the contracted with the tensor, and this one, and we're going to identify this anti-symmetrization of the Christoffel symbols as this other tensor here, this 1, 2 tensor here, okay? And we're gonna, this guys are gonna be very important, right? We identified both tensors in red and blue. The tensor in blue is what we call the Riemann tensor. And the blue, let me just check. Yes, the red tensor is what we call the torsion tensor, right? Such that we define the Riemann tensor as follows. Another one, so you see, I put this in a block here in the presentation, the same way I did the Christoffel symbol definition with respect to the metric, which means that this is going to be a recurring character in this season. It's going to be a recurring character in the next lectures, okay? Very important to remember this definition, right? In our space-time, in the case that we're working on, right, in classical general relativity, we assume that we have a connection without torsion, which means to make this tensor equal to 0, which means to say that the anti-symmetric part of the Christoffel symbols are 0, which means that the Christoffel symbols are symmetric in the two lower indices, right? So which means that gamma mu nu is equal to gamma nu mu, right? Which simplifies a lot, because when we are working with solutions of Einstein's equations and so on and so forth, we have to calculate this guys here so we can know how freely falling objects move, right? The geodesic equation, this guy is a protagonist in the geodesic equation. So we have to calculate these guys, which we know how to do, right? If you have a metric, We know how to compute these guys here, but we don't have to compute every single one because we know that, for example, the components 0, 1 here are going to be equal to the 1 zeros, right? So this saves us a lot of trouble. This symmetric, anti-symmetric parts, and so on and so forth, they save us a lot of time in the computations, which will be long no matter what, but it becomes a little bit less nasty, I think. So if we set this torsion tensor equal to 0, what we have is this, right? The commutator of the two covariant derivatives acting on a vector is given by this. So the Riemann tensor exactly contains the information on how curved our space-time is, right? Because if this commutator were 0, see, if this commutator were 0, this would mean that the subsequent applications of the covariant derivatives are 0, which means that the tensor here, when transplanted through this closed loop, would be the same, which means, as I already said earlier, that our spacetime is flat. So the existence and the fact that this tensor is not 0 is directly related to the fact that our surface or spacetime, or I mean, the surface that we are analyzing is curved. Okay, our spacetime, our manifold is curved. Okay. So here are some properties of the Riemann tensor that I'm not going to prove here because I have very little time and a little bit of ground to cover still. But these are some properties that you can prove. I know that I'm acting like those sentences in books that we all much love, that proof is left to the reader, right? But in question concerning time, we don't have time to do these proofs. But you can do it. And if you have any questions about the proofs, you can always ask me in a future lecture. There will be no problem. We can work this out between lectures and so on. Okay. But these are very important properties. So see that if we lower the index, right, the contravariate index of the Riemann tensor with the metric, so this guy is not the original Riemann tensor, right? We're gonna have to imagine here that we took the metric, right, in the previous here. We took the metric and we contracted with this with this index, and we lowered it. Okay. So in this version, the properties are very much more they're more easy to see. That these two indices are anti-symmetric between them, and these two indices are symmetric between them. Okay. We can change the pair. So this tensor is symmetric between the exchange of the two pairs, but in the exchange of single indices, so this one with this one, it is anti-symmetric, and this one with this one is anti-symmetric as well. Okay. And the most important maybe property of the Riemann tensor is this one, which we call at least one of the Bianchi identities. Okay. Contracting the first and third indices, which means to do this, which is the Kronecker delta, right? What the Kronecker delta does is just relabel indices, right? So you see that it is contracted with alpha here in a way that we change alpha to rho, which is the same as to change alpha to rho, rho to alpha, right? Is the same thing. The two indices are contracted, which means that there's a sum here, right? And these two dummy index may go away. And now by contracting two indices of a rank 4 tensor, right? We obtained a rank 2 tensor, right? A 0,2 tensor. So we departed from a 1,3 tensor to a 0,2 tensor by contracting the first and third indices, right? And this tensor is as well very important, and it's called the Ricci tensor, right? It also has information on the curvature, right? But you have to see that you can see that we lost a little bit of information right here, but we can always gain back this information, right? Through a inverse operation and so on with the tensors, right? But the Ricci tensor is exactly defined by this, which is obtained by contracting the first and third indices of this expression, right? Another proof that one could do to see that it is correct is perform this contraction and see that you get this, all right? If it is in a block, it means that is a recurrent character in the next episodes, in the next lectures. So very important also to remember this definition. And subsequently, we can contract these two indices also, right? We have to raise this index and contract with the other, and we would get it a scalar, right? Which we will call the Ricci scalar, right? Which also contains information on curvature, but less information than the Ricci tensor and less information than the Riemann tensor, right?
Vitor,
Oi.
João Pedro asked, why do we contract the first and third indexes specifically? Could we contract the first and second?
Yeah, well, this is a question that comes a lot, that is very common. Well, the thing is, the Riemann tensor is not defined the same way depending on the references, right? So if you go to Wald, for example, you're gonna see a different form of the Riemann tensor here. You could have the fourth index raised, and this one is lowered, and so on and so forth. This is something that have troubled me before. I mean, because in some references, in the definition, you could, in principle, a priori contract other two indices. But in this definition, I guarantee you that if you do this, contract this first and third indices, you're gonna get the correct Ricci tensor. If you do it differently, because of these properties, you're gonna have different tensors which are not the Ricci tensor, which are not defined as this, right? And this is something that always confused me. So I'm gonna ask you, João Pedro, to let me get back on you, get back to you on that for sure. But I mean, I don't know, Victor, if you have a definite answer for this, different than mine, you could jump in and answer if you like.
I mean, from the top of my mind, I can't think of anything differently than what you said, but considering maybe he didn't understand what you've explained, we can, I don't know, take a look at it later, and on the next lecture, we can start with this question. But from his
Yeah,
comment, he said, got it, thanks. I think it is clear
yeah.
now.
Yeah, well, it's not a trivial question. Bear in mind, it's a very good question because I don't know, but from the back of my mind, I remember reading somewhere. I don't remember where, saying that it doesn't matter which indices of the Riemann tensor you contract, you're going to have the same tensor. But I tried to do this by hand, and this was not at all my experience, okay? So with this definition here of the Riemann tensor, if you contract two different indices, you're not going to have the same tensor as the Ricci tensor here, right? You can try this at home by yourself, and you're going to see that it is a different tensor. One could say that they are equivalent, and that is the thing that maybe is what someone meant by oh, you can contract any two indices and so on and so forth. But I have to get back on this. Yeah, basically, yeah, that's it. You have to stick with the convention, right? So it depends. In this convention here, in this form of the Riemann tensor, you have to contract the first and third indices. If you go to Wald, he's gonna contract. I think that he contracts two different indices, not the first and third. But I mean, the interpretations, the views are equivalent, right? There are no different physics in doing so. But here you have to contract the first and third to obtain the Ricci tensor, right? But I'm gonna get back to you on that with more details in a future lecture. So okay, so now we have all the ingredients to get to the Einstein equations finally. And there are a lot of ways to do so, but I think the most straightforward way is to go to the Einstein-Hilbert action, construct the Einstein-Hilbert action, and, well, turn on the machinery of the Euler-Lagrange equations and see what the equations of motion look like, right? I'm not gonna tell you why. I'm not gonna prove to you that this is the right action to take that will take us to the Einstein equations. But you can also check this in Carroll is a very good treatment, I think. Poisson, I think the book by Poisson also does this. But I think I remember learning this from the book from Carroll, right? Space-time and geometry. It has a very straightforward and clear train of thought about the variation, how to take the variation of all these objects here. But basically, this action would be the simplest action that you could construct from a scalar that contains information about curvature of your space-time, right? So we wanna develop a group of equations of motion that bear in mind the curvature. So this would be, I think, the simplest action that you could construct, right? You could construct different scalars from the Ricci tensor, the Riemann tensor, but this is the most simple action that you could do. And then turning on the machinery of Euler-Lagrange. Oh, yes. So this matter, this action is respective to the curvature space-time, right? In vacuum. But if you want to include matter, you just include some action to this action, right? You include this other SM, and now we turn on the machinery of Euler-Lagrange equations, varying S with respect to G mu nu, right? With respect to the metric, and setting the variation equal to 0. And then what we get is the Einstein equations, right? In here, we have to define T mu nu here as this object here, which is the variation of the matter action, right? With respect to the metric, and this coefficient here, which here G is the determinant of the metric, right? And in such a way that now we have the the energy momentum tensor of the matter that you included in your space-time, and now we have the Einstein field equations, right? And it's very important to try and understand what the Einstein equations are trying to tell us, right? And I have no other, I've never seen a better way to describe this than the John Wheeler quote that states that matter curves space-time, and curved space-time tells matter how to move, right? So matter tells space-time how to curve, and curved space-time tells matter how to move. We're gonna see the second part of this statement is gonna be clear in a moment, but I don't know if I have to do this here. So the first part of the statement, matter tells space-time how to curve, is very clear here from the Einstein equation, because from one side of the Einstein equation, we have matter, right? Represented by the tensor T mu nu, okay? In the other side, we have the Einstein tensor G mu nu, which is constructed thusly, right? With the Ricci tensor minus the metric, half the metric, multiplying the Ricci scalar, right? So in the right side, we have matter. In the left side, we have curvature. So matter tells space-time how to curve. But remember that inside the definition of these guys here, of these elements, we have the Christoffel symbols, right? And from the Christoffel symbols, we are able to construct the geodesic equation, right? Which tells us how free objects, which tells us the paths of freely falling objects in our space-time, right? Objects free of external forces. So this is what John Wheeler means by the second part of the statement, that curved space-time tells matter how to move, right? Because curved space-time is what allows us to construct a notion of how the geodesics in our space-time are. Okay, so the path is you add matter to your space-time. This matter is gonna curve your space-time. The space-time around is gonna be curved. This curvature is gonna be embedded in an element called the Christoffel symbol, which finally is gonna be embedded in the equations of motion of freely falling bodies in our space-time. Okay, so once more, I'm gonna repeat it. The John Wheeler quote, which is, matter tells space-time how to curve, and curved space-time tells matter how to move. Okay. Well, now we have the Einstein equation. I'm finishing. All right, I'm almost finished. I think the next slide is the last one. So what it means to solve this equation, right? So inside this, guys, we have the Christoffel symbols, but inside the Christoffel symbols, we have the metric, right? So what we are doing here when we solve the Einstein equation is solve for G, right? G is the variable for which we are going to solve, right? The components of the metric are the variables of this differential equation, a nonlinear, right? Highly nonlinear differential equation. So to solve this, it means to solve for the metric components, right? The G mu nu, right? Because, well, if you do so, if you obtain as the answer the G mu nu, you know how to construct the Christoffel symbols and so on and so forth. But basically, G mu nu is the most fundamental of the objects represented here, because it is through the G mu nu components that we are able to construct an invariant notion of distances in our space-time, right? Remember the line element, it is, yes, here. We are only able to construct an invariant way to measure distances in our space-time through our components G mu nu. So it is the most fundamental of objects represented here, right? And the way to measure distances is intrinsically related to how the space-time is curved, right? So to solve the Gaussian equations is to solve for G, and here are some notable solutions of Einstein's equations. One of them is the Minkowski spacetime, which is the flat metric, which represents a spacetime with no curvature, right? So you see here that G mu nu is completely, all the elements, right? Well, all the metric components are constant here. I mean, I know that here we are not in a format that is clear, right? Here we have a r squared, but this could also be written as less of minus dt squared plus dx squared plus dy squared plus dz squared. This is in spherical coordinates, but if we transform this to Cartesian coordinates, remember that the metric components will change, but the tensor, the object, the bold G will not change, because the basis of this tensor will change with exactly the inverse transformation, right? So if we change this this metric to the Cartesian coordinates, this would be minus dt squared plus dx squared plus dy squared plus dz squared. In this form, in the Cartesian form, you see that all the components of the metric are constant, which means that the Christoffel symbols will be zero, right? Since the derivatives with respect to anything will be zero, right? Which means that the Ricci tensor, the Riemann tensor will be zero as well, right? Which means exactly what I said earlier, said before, that Minkowski space represents a space-time with no curvature, right? And last, another notable solution is the Schwarzschild spacetime, which is to solve the Einstein equations, assuming that that we are solving for the exterior of a spherically symmetric object. So this could be a star, this could be a planet, this could be any spherically symmetric object. This solution represents the space-time outside of this object. So this means that both of these solutions are vacuum solutions, which means to set T mu nu equal to zero, right? So this equals to zero, and then we have an homogeneous differential nonlinear equation, nonlinear differential equation here, set of nonlinear equations, right? Because for every value of mu and nu here, we have an equation. So the Einstein equation are here in plural Einstein equations, because this is a set of equations, right? So here, the Schwarzschild spacetime is exactly this. So it is the geometry, it gives us the geometry outside of a spherically symmetric object. Okay, and these are the two metrics that we're going to do perturbation on in the subsequent lectures. First, we're going to start with this metric. I'm going to do perturbation here, see what the gravitational waves in this kind of space-time look like. And later, we're going to do the same here with the Schwarzschild space-time and see what the gravitational waves from this space-time look like. Okay? Well, this finishes our journey through general relativity. and also finishes this lecture. I thank you all for the attention, for the questions. The questions always enrich the lectures very much. So don't be afraid to ask them. Don't be afraid to I don't know, to throw at us any question that you have. If I don't have the answer right away, I promise that I will look into it and give it to you guys later. So there's no shame in here. If I don't know right away, I will tell you and try to get the right answer, the correct answer in a later lecture. But so that's it. I see you guys in the next lecture where we're gonna talk about GR in the weak field limit. And we're gonna start now we're gonna actually, in the next lecture, we're gonna actually start to look into gravitational waves, and we're gonna see how the general relativity, the theory of general relativity, predicts the existence of gravitational waves. Where does it come from, right? This prediction, where is this prediction inside the theory? And we're gonna see this in the next lecture. So that's it.